Jai Hind everyone. I am Vikas Rathi, working in Ajay Kumar Garg Engineering College as an assistant professor. The subject which I am going to discuss is engineering physics. Subject code BAS 101 / BAS 201. Means in first semester it is BAS 101, but in next sem, that means in even sem, it is BAS 201. Now the topic which I am going to discuss is Maxwell's equations and their physical significance, and this is part of the electromagnetic field theory, which is here in this subject unit 3. So the topic is Maxwell's equation and their physical significance. References: there are many references for this topic and for this unit. Like Introduction to Electrodynamics by D.J. Griffith, okay, Concepts of Modern Physics by Arthur Beiser, Engineering Physics of Theory and Practical by Katiyar and Pandey, Applied Physics for Engineers by Neeraj Mehta, and Engineering Physics by H.K. Malik and AKGE. So these are the references, and this is the main reference for this topic, right? Electrodynamics by D.J. Griffith. There are many topics in this unit, like continuity equations for current density, displacement current, modifying equation for the curl of magnetic field to satisfy continuity equation, Maxwell's equation in their integral and differential form, their physical significance, electromagnetic wave equations in free space, transverse nature of electromagnetic wave equations in free space, relation between electric field vector and magnetic field intensity vector, that means E and H. Other topics are Maxwell's equation in non-conducting medium, skin depth in conducting medium, Poynting vector and Poynting theorem, energy and momentum carried by electromagnetic wave, and radiation pressures. So these are the topics in this unit, but today I will discuss Maxwell's equation and their physical significance. So today topic is Maxwell's equations and their physical significance. So what are Maxwell's equations? Maxwell's equations are a set of 4 differential equations that form the theoretical basis for describing classical electromagnetism, right? And Maxwell's equations, they are based on 4 laws: Gauss law of electrostatics, Gauss law of magnetostatics, Faraday's law of electromagnetic induction, and Ampere's circular law. Okay, basically this Ampere's circular law is here the 4th equation is basically modified form of the Ampere's circular law, right? So whole electromagnetic theory is based on 4 Maxwell's equations, and these Maxwell's equations are basically Gauss law and Faraday's law and Ampere's law. Okay, so whole theory is based in these 4 laws. So these are the basic bond of this electromagnetic field theory. Now I will start with first unit, first Maxwell equation. Okay, so we can write here these equations in their integral form. Then by using Gauss divergence theorem and Stokes theorem, we can find out their differential form. So there are some mathematical formulation to find out the integral and differential form, because Maxwell's equations in mathematical form can be written in their integral form and in their differential form. So according to Gauss theorem or Gauss law, we can write this Gauss law in this mathematical equation. Here this integral over a surface S, E dot ds equal to Q divided by epsilon naught. Here this E dot ds, this quantity represent electric flux, which will be equal to charge. This charge is here charge enclosed within that surface, divided by epsilon naught. Epsilon naught is the permittivity of the free space. So this equation 1 represents here Gauss theorem or Gauss law in integral form. Now to write the integral form of this law in a proper form here, according to definition of the current density, we can write this Q in terms of the current density rho. Here this rho, this is the current density, this quantity represents current density. So equation 1 will be here, left hand side remains same, that means E dot ds over a surface S, this will be equal to here Q we can replace with this according to definition of the charge density. Here Q, this is the charge density means charge per unit volume. So charge density, or you can say charge, can be written in terms of the charge density in integral form. So Q will be equal to rho dot dV over a volume V. So if we replace this Q with this quantity here, now the equation becomes this right hand becomes 1 by epsilon naught integral or a volume V rho dot dV. Now to find out the differential form, here we can use Gauss divergence theorem. Gauss divergence theorem can be used to convert the surface integral into volume and volume into surface integral. So here left hand side of this equations can be converted into, which is in surface integral form. We can convert this left hand side of this last equation or equation 2 in volume integral form. So according to Gauss divergence theorem, here this quantity E dot ds over a surface S, this will be equal to volume integral over a volume V del dot E dV. Here this del dot E means here this will be the divergence of this physical quantity, and physical quantity is here electric field. So that means if we want to convert, if we require that we want to convert some surface integral into volume, so that means we have to take the divergence of this vector quantity. Okay, so here this left hand side will be now in terms of the volume integral. So this del dot E here divergence in short form, this can be written dVE, means divergence of this vector quantity. So by using Gauss divergence theorem, we can convert this surface integral into volume. So we have to take the divergence of this physical quantity, and physical quantity is here in our case electric field. So now we can substitute this value in last equation, that means in equation 2. So now this left hand side, it will becomes volume integral over a volume V del dot E dV, and this will be equal to this much 1 by epsilon naught volume integral over a volume V rho dV. So right hand side becomes as it is. Okay, or we can write this, we can take this inside this integral, this quantity epsilon naught, so this will becomes in this form now, right? Or we can write this last equation in this form. Here it is written directly, so we can write this volume integral over a volume V del dot E minus rho by epsilon naught dV equal to 0. So we can write this last equation in this form. Now for any arbitrary surface, we can vanish this integral sign. So this last equation now becomes in this form, this, right? So del dot E equal to rho divided by epsilon naught. Or if we multiply this rho naught in left hand side, okay, now this equation becomes del dot epsilon naught E equal to rho. And now here we can introduce new quantity which is d here, and this is known as electric displacement vector d. So we can write this equation or this law, Gauss law, in differential form by using Gauss divergence theorem. Okay, so these are the forms. Here we can write this law in differential form like del dot E equal to rho by epsilon naught, or we can write this law in electric displacement vector d, so del dot d equal to rho. Okay, so these are the differential form. Okay, so we have Maxwell's equation in their integral form and in their differential form, right? So now physical significance, what this last equation means, this first equation, first Maxwell's equations represents, we can write their physical significance using this integral form of these equations. Here this left hand side, this represents electric flux quantity, basically electric flux phi E. Okay, so that means here we can say the physical significance of first Maxwell's equation is the total electric flux over closed surface is equal to 1 by epsilon naught times charge enclosed within that surface. Means this quantity basically represents here charge. Charge means charge enclosed within that surface. So electric flux, total electric flux, okay, over a closed surface will be equal to 1 by epsilon naught times total charge enclosed by that surface. So here this integral, the Maxwell's equation in integral form itself represents the physical significance of this Maxwell's first equations. So again I will repeat, significance of this equation is total electric flux over a closed surface is equal to 1 by epsilon naught times total charge enclosed within that surface, right? And finally this is the integral form here of this Maxwell's first equations, means E dot ds over a closed surface S equal to 1 by epsilon naught volume integral over a volume V rho dot dV, and differential form in terms of electric field is del dot E equal to rho by epsilon naught, and in terms of electric displacement vector D, this is del dot D equal to rho. So this is all about the first Maxwell's equations. Here we learn about the differential and integral form of these equations and its physical significance. Now I will discuss next Maxwell's equation 2, okay, second Maxwell's equation, which is basically Gauss' law in magnetostatics, okay. So here we will discuss the significance. We know that magnetic monopole does not exist, or we know that magnetic induction across any closed surface is always 0. So by using these facts we can write this in integral form, which is B dot ds over a closed surface S equal to 0. We can put here close sign, okay. So this is the Gauss' law in magnetostatics, okay. Now we can find out, this is the integral form of this equation 1 represent integral form of the Maxwell's second equation, right. Now to find out the differential form of these equations, again we will use Gauss divergence theorem, and we know that if you want to convert surface integral into volume integral, that means we have to take the divergence of that vector quantity, and vector quantity is now here B, which is magnetic field density vector B. So that means left hand side means B dot ds over a surface S, this will be equal to, here we will put volume integral over a volume V and del dot B, that means divergence of, we can write this like this, volume integral over a volume V, divergence means dV of B into dV. That means we have to take the divergence of that vector quantity if we want to convert the surface integral into volume integral. So now from equation 2 and 1 we can put this equation in this form, means surface volume integral over a volume V del dot B dV equal to 0. Now again for arbitrary surface we can vanish this integral sign, that means we can write this equation without integral sign, that means now this equation, last equation becomes del dot B equal to 0, that means divergence of magnetic field vector B equal to 0. Now we can introduce here new quantity, here this magnetic field intensity vector H, because we know that relation between magnetic field density vector and magnetic field intensity vector is in free space is B equal to mu naught H. So if we want to write this equation in terms of this new quantity, new vector h, then we have to replace this here. Okay, we can multiply this mu naught. Okay, mu naught is here permeability of the free space. So now this quantity, okay, becomes, or finally we can write here in this form, this equation, del dot h equal to 0. So here we have the differential form of this equation. So again, by using Gauss divergence theorem, we can find here the differential form of this equation, second Maxwell's equation in terms of the B vector and H vector. Okay. Now we can here write the physical significance of this Maxwell's second equation simply by seeing this equation here. Okay, Maxwell's Gauss law in magnetostatics, which is B dot ds over a closed surface S equal to 0. So significance of this equation is basically here this B dot ds over a closed surface S, this is the magnetic flux phi b. Okay, so that means total magnetic flux across any closed surface is always 0, or magnetic monopole does not exist, right? Means, okay, magnetic, or we can write here magnetic lines of forces, they are basically continuous. So change in magnetic flux will always 0, or magnetic monopole does not exist. Okay, so these are the significance of the Maxwell's second equation. Okay, again here magnetic monopole does not exist because magnetic lines of forces, they are continuous. If they will start from the north pole, then they will end on the again on the north pole, right? So they are continuous. So change in magnetic flux will always 0. That's why we can say magnetic monopole does not exist. If there will be north pole, so south pole must always exist there, right? So this is the integral form, and these are the differential form, del dot b equal to 0, or in terms of the magnetic field intensity vector, del dot h equal to 0. So this is the this is all about the Maxwell's second equation, their form, integral form, and their differential form, and the physical significance. So we can write Maxwell's equation in integral form, in differential form, and in different in form of the different vectors, right? So this is the Maxwell's second equation. Now I will come on Maxwell's third equation. Maxwell's third equation is basically Faraday's law of electromagnetic induction. Okay, this is not a new law. This is not a new new law here. This is basically the Maxwell's third equation. So according to Maxwell's, Faraday's law of electromagnetic induction is the Maxwell's third equations. Now again, we will write according to the Faraday's law of electromagnetic induction. We can write EMF, induced electromotive force in a closed loop is given by decrease or negative rate of change of magnetic flux. So here E, this represents induced EMF. This quantity E represents induced EMF, which is equal to minus sign represents here rate of decrease, or okay, negative times rate of decrease of magnetic flux. This phi b, this is the magnetic flux here. So Faraday's law of electromagnetic induction, according to Faraday's law of electromagnetic induction, we can write this in mathematical, in this mathematical equation. Okay, so EMF equal to minus rate of change of magnetic flux. Okay, so E equal to minus d phi b by dt. Okay, now to find out the differential form of these equations, okay, if you want to find out the differential form, then we have to take we have to use some theorems, like we will use here Stokes theorem, Okay, previously we used Gauss divergence theorem. Now here we will use Stokes theorem, because Stokes theorem can be used to convert the line integral into surface or surface into line. So this is required here for our case. So now according to definition of electromagnetic force, EMF, this this can be written in terms of the electric field vector E. So this is E dot dl over a closed curve C. This is equal to minus d phi b by dt. So right hand side this will remain same. Or according to definition of the magnetic flux, which is phi b can be written in terms of the magnetic field density vector B, which is surface integral over a surface S B dot ds. So we can replace this quantity phi b in terms of the magnetic field density vector B in right hand side of this equation. So right hand side of this equation now becomes minus d by dt surface integral over a surface S B dot ds. Okay, so this will becomes now in this form. Now we will do some mathematics here again. So this left hand side means line integral over a closed curve C E dot dl. This is equal to surface integral S, and this is minus d del b by del t into ds. We can write this in this form. So this is suppose equation 2 now, right? Now according to Stokes theorem, Stokes theorem, as I have told, can be used to convert the line integral into surface and surface into line. So here left hand side in our case is E dot dl over a closed curve C. This will represent, this L represents here line integral here basically over a closed curve C. So this will be equal to surface integral del cross E dot ds. Del cross me means here this is basically curl of this vector quantity E. So we can, in short, we can write this equation in this form: surface integral over a surface S, curl of this vector quantity is your electric field, okay, or into ds. So in del operator, this is basically del operator, this del quantity, this is the del quantity. So if you want to curl, if you want to take curl of any vector quantity, then we have to take the cross product of del with that vector quantity. Okay. Now this line integral converts into surface integral, and this equation now becomes E dot dl over a closed curve C, okay, or line integral L. This is equal to surface integral over a surface S del cross E into ds. So now we can put the substitute this value in last equation 2. So this left hand now of equation 2 becomes surface integral over a surface S del cross E dot ds equal to surface integral over a surface S minus del dB by dt into ds. So this right hand side remains as it is, but by using Stokes theorem we have to convert here line integral into surface integral, and again to convert the line integral into surface we have to take curl of that physical quantity, that physical vector quantity, okay, and curl means here del cross E. E is here that physical quantity, right? Then again we can write this last equation in this form: surface integral over a surface S del cross E, and in left hand side it will becomes plus del dB by dt into ds equal to 0. So to get this form, this last equation, here we have to put this equation in this form, okay, then we can write without integral sign. That means here for arbitrary surface we can always vanish this integral sign, and without integral sign, that means now this equation becomes del cross E equal to minus del dB by dt, right. So this is the differential form of the Maxwell's third equation, which is also known as Faraday's law of electromagnetic induction, right. Now to write this equation in another quantity, in form of the another quantity which is H, we know that this relation B equal to mu naught H, in free space, where mu naught, this is the permeability of the free space. So that means del cross E equal to minus mu naught dH by dt. So these are the differential form in terms of the B vector and in terms of the H vector. Now finally, what is the physical significance of this equation? So we will discuss physical significance of this equation, right. So as you know, here this integral form itself represent the physical significance of the Maxwell's equations. Here we know this left hand side, basically this represents EMF, induced EMF, which is represented by quantity E, small e, and here this was written minus del phi b by del t. So here this law, Faraday's law of electromagnetic induction, which is induced EMF equal to minus rate of change of magnetic flux, represents physical significance of Maxwell's third equations. So what we can write this equation, equation third here, which is Faraday's law of electromagnetic induction, and it signifies that an electric field is produced by changing magnetic flux, or induced EMF will be equal to minus rate of change of magnetic flux. So we can represent the physical significance of the Maxwell's third equation, by using the integral form of this equation. Now here we have already find out the differential form of this equation, which are del cross E equal to minus del dB by dt, right. And in terms of the H vector, this is del cross E equal to minus mu naught times del H by del t, where again this mu naught is known as permeability of the free space. So now we know about the, in detail we know about the Maxwell's third equation, its integral form, its differential form, right, and its physical significance. So it is not a new thing, it's basically based on the Faraday's law of electromagnetic induction. So in detail, just we have to find out the differential form of the Faraday's law of electromagnetic induction by using the Stokes theorem. So by using the Stokes theorem, we can find out the differential form of this law, right. So this is the Maxwell's third equations. Now we will discuss last Maxwell's fourth equation, right. Maxwell's fourth equation, this is basically Maxwell's fourth equation is also known as modified Ampere's law. We know the Ampere's circuital law, and modified form of the Ampere's circuital law is known as Maxwell's fourth equations, because it was modified for the free space. If there is a conducting medium, then circuital law is applicable there. If there is a free space, there is vacuum, then that circuital law is not complete, right. So means here by using fourth to discuss this Maxwell's fourth equations, we have to write down the modified Ampere's law, and which is B dot dl over a closed curve C, this is equal to mu naught IC plus ID. Here this IC represents here conduction current, and this ID represents here displacement current. Now according to definition of the displacement current, this ID, this can be written here epsilon naught del phi E by del T. Okay, this phi E, this is the electric flux. Okay, so because the origin of the displacement current is change in electric field or electric flux, so in terms of electric flux or in terms of electric field, it can be written in this form here. Okay, so now according to definition of the current density, which is this quantity J here, current density means current per unit surface area. Okay, so according to definition of the current density, it can be written, this IC can be written J dot ds, okay, or a closed surface S here. So again we can write IC in this form. Okay, this is surface integral over a surface S J dot ds plus epsilon naught del by del T, and again we know that this electric flux can be written E dot ds over a closed surface S. So by using the definition of the current density here, okay, charge density, definition of electric flux, magnetic flux, we can change their form. Now we can combine this, we can take this mu naught here common, then they will becomes in this form. Now equation 2 here, suppose this is equation 2. Now we can convert this line integral into again surface integral by using the Stokes theorem. That means we have to take the curl of that vector quantity, and vector quantity is here B, magnetic density vector B. So means surface line integral over a line L B dot dl now becomes del cross B, means curl of this quantity. This del represents curl of this quantity B here. Now we can substitute this value in equation 2. Okay, so equation 2 now becomes this del cross B over a surface S ds, okay, equal to this much mu naught times J dot this plus epsilon naught E by dt. Okay, so here this is a mistake, you can write this mu naught here basically. Okay, or again we can write this equation here surface integral over a surface S del cross B, okay, minus mu naught J plus epsilon naught dE by dt into ds equal to 0. And we can here replace this, we can vanish this integral sign. So then this will becomes here del cross B equal to mu naught J plus epsilon naught dE by dt, or in terms of H vector, this is del cross H equal to J plus epsilon naught dE by dt, because we know that in free space B is related with H vector by this equation B equal to mu naught H. Now we will discuss the significance, okay, significance of this equation, physical significance of this equation. Okay, physical significance here, basically Maxwell's fourth equation represents the modified form of Ampere's law, Ampere's circuital law, and this equation shows that magnetic field can be obtained by conduction current as well as by changing electric field. So means magnetic field can be produced by both conduction current as well as by changing electric field, right? So this is the significance, physical significance of this equation. Now integral form, as we have already find out, this is the integral form of this equation. B dot dl over a closed curve C or line integral L equal to mu naught times this surface integral over a surface S J plus epsilon naught dE by dt dot ds. Okay, and their differential form, as we have already find out, del cross B equal to mu naught J plus epsilon naught dE by dt, or in terms of H vector, this is del cross H equal to J plus epsilon naught dE by dt. So this is all about the Maxwell's fourth equations. Okay, Maxwell's fourth equation is basically modified Ampere circuital law, right? So this is about the Maxwell's equations first, second, third and fourth. Now there is application of these Maxwell's equation. By using Maxwell's equation, we can find out different other equations here, like continuity equation can be obtained by using the Maxwell's fourth equations. So by using Maxwell's fourth equation here, we can find out the continuity equation. So this is, we know this is the differential form of the Maxwell's equation, okay, or in terms of H vector, this is del cross H equal to J plus epsilon naught d by dt. Now taking the Gauss divergence of this equation 1, divergence means we will take dot product of this with vector del. So del dot del cross H will be equal to del dot this much, or if we multiply this, if we open this, then it will becomes del dot J plus del dot epsilon naught d by dt. Now we know this vector identity, that divergence curl of any vector quantity always 0. That means this left hand side always becomes 0. If this is 0, then we have to put here right hand side will be equal to 0, okay, and this will be equal to 0. Then we will have equation here in this form, means del dot J plus epsilon naught, this del dot E divided by del T equal to 0. And from Maxwell's first equation, we know that Maxwell's first equation in differential form is this much. So we can replace this value with the charge density rho, okay, or finally this will becomes here, this rho naught will cancel out, and del dot J plus d rho by dt equal to 0, or del dot J equal to d rho minus del rho by dt. This equation third, this is known as continuity equations. So there is a lot of applications of these equations, okay. So this is one of them, right. So thank you. We will meet in next lecture. Thanks a lot.